Okay, so we consult. So we know that the shear flow is controlled by the web. So these are coming down. Okay, and then go out. Go out. Hey, wrong direction. So over here is a terminal. And over here and here are also our terminal. Okay, all right, okay. So from here, we know that tau max is equal to 10 times 10 to the power 3. And we know that our formula for tau is equal to VQ over IT. Okay, VQ over IT. Okay, so let's start by looking at the shear flow. Okay, let's find. But before we do anything, right? We also, so there are in fact there are three things we have to determine. Okay, so there are three things. We want to find the shear stress at point A, right? Shear stress at point B, and we want to find the location of maximum shear stress. Right? Only if we can find the maximum, then we can apply this equation. Okay. So V and I are constant. So at A, B, and at tau max, V and I are always what? Constant. Okay. I realized when I mark your term test, some of you did not follow that rule. You start dividing the loads, and then you get confused, and that's where mistake happens. Okay. So stick to these rules, you'll be fine. Okay. Right. So now let's do the analysis. Okay, so we're going to find the stresses at point B first. Okay, let's find the stresses at point B. So I'm going to I need a blank. Hold on, bear with me. PowerPoint. I need to draw a box. And yeah, choose a better color. Okay. Copy. Okay. So remember the rules that we have is that the first moment of area cannot cross the centroid. Okay. So based on geometry, right? This is our centroid. Centroid is exactly at the center, 1.5, exactly. Okay. That's our centroid. Okay. So now we are going to find. Okay, we are going to find. Okay, what we're trying to achieve down here is we're going to find. Let me copy this again and then paste this elsewhere. Okay, we're going to find the shearing stress at point B. Okay. So now this looks confusing, right? Is it a white a box beam or white flange? So now I cover here, right? And then I construct the shear flow. Right? And then we have a terminal. And then you have Q going to one side. Right? You have the other Q going to the other side from one terminal. Right? So this is from one terminal. we have one Q going to one side, the other Q going to what? The other side, right? Okay, question for you guys. Is this a box beam or wide flange analysis? Anyone? Box beam or wide flange? Hello?
I'm not sure, but wide flange?
No, it's box beam. I'll tell you why box beam, okay? You cheeky sort, yeah? You're doing 50-50, yeah? I'll tell you why box beam, okay? So if you look at the structure now when I cover the bottom, okay? Right? And then if you look over here, right? Why is it box beam? Because it starts with one terminal and the Q splits into left and right. It goes away from the terminal. If it's I-beam, will be two terminals, the Q will come together. So that's why it's called a what? Box beam analysis. So this is a box beam analysis, okay? So from here, we're going to apply box beam analysis. Okay, box beam analysis. And at this stage, if you look at the Q from one terminal, right, the Q goes into left and right, right? So you put that you have to have two Q over here, right? Because one Q go to the left, one Q go to the right. And now the thickness, because it's thin wall, okay? So all this, I'll write down thin wall analysis. Thin wall, okay, you know what? I like apply thin wall box beam analysis 2Q. Okay, 2Q because of left and right down here, yeah? I will put the arrow down here, Y2Q1. Okay. So the thickness now, so the thickness is perpendicular to the shear flow direction, so it's 0.2 inches. Okay. So the next thing is find the first moment of area. Okay, so we're going to find the first moment of area. Okay. So the area that you have to consider is this entire area down here, where I'm shading in red. Okay, this entire area. Okay, so if I string this box, right, we can, I need to string more point. No, I think this is enough to show us the dimension. Okay, so Q is equal to width multiplied by depth y bar. Okay, so my width is equal to 2 minus by 0.3 minus by 0.3, right? The depth is 0.2. The y bar is 1.5 minus 0.2 divided by 2. All right. So 2 minus 2 minus 0.3 minus 0.3 times 0.2. So it's 2 minus 0.3 minus 0.3 times 0.2. So 0.28 multiplied by 0.2 divided by 2, 1.4. So this is 0.28 times 1.4 is 0.392 inches to power of 3. Okay. So the shear stress at point B, right, at point B is equal to VQ over IT, right? So V, we don't know what is V yet. I, we did not find yet. It's okay. Okay. I say it's okay because later on they will cancel it. Okay, they'll cancel out. But if by accident you find what is A, don't beat yourself over it. You find find what is I, find what is I, it's fine. Okay. So Q is equal to 0.392. We know the thickness is equal to 0.2, but you have to multiply by 2 over here because we have what? 2Q. Okay. So now this is V over I, or 0.392 divided by 2 divided by 2, 0.98. Wait, 0.392 divided by 2 divided by 2, 0.98. So 0.98 V over I. Okay. That's at point B. Now we're going to find the shearing stress at point A. Okay. Before I go on, anyone, any question with this? Anyone? It looks easy, right? No problem. Yes. Okay. Then we go into point B. Yeah, we go into point B now. Sorry, point A. Okay. So next, we want to find. Okay, find the shearing stress at point A. Okay, and find the shearing stress at point A. So same thing, right? Now it looks confusing, right? Oh, if you look at point A, oh no. Okay, I was also very confused. Okay, when I taught this topic the first time. When I taught this topic the first time, it was a nightmare. Okay, it was not easy to understand. So remember this: if it's not easy to if the professor is not explaining a way that's easy to understand, okay, he himself or she herself is also confused. Okay, from experience. Okay. Okay. So now we want to find point A now. Okay. But do not be rude to those instructor that you feel that they don't know what they are teaching. Okay, be nice. Okay. Okay. So now I cover the top. Okay, I cover the top. Question for you: is this white beam? Sorry, is this box beam or white flange? So I'll still construct the shear flow, right? Okay, I'll see. White flange. You're right. Yay, you got it. I'm most happy. Right? Right? Okay, so you know it is white flange. Right? Then the confusing part comes when I did this problem the first time. What area I take? Right? What is the area I take? So remember, the analysis starts from, so if we look at one of the rules we have, right, the analysis starts from, so this is the analysis direction. Right, that's our analysis direction. So if you follow the arrow, right, based on the analysis direction, this is the area that you have to consider only. Because of where A is, right, this is the area. Right, and you will see down here, this is our terminal. They both start from different terminal or end in different terminal. This one at this terminal, I call it terminal 1. This one is terminal 2. So what happened in terminal 1 is independent from terminal 2, right? They're not linked at all, right? So when this is the case, right, you are going to do your analysis. Okay, so the analysis So we're going to find the shearing stress at point A. So the analysis, right? The analysis is